and that I want to make sure some things that we've talked about you've acclimated to appropriately. So I want to put something on here, and I want to see if you are successful at it. Let's just say that maybe this could have been what I put on your quiz. It wouldn't have been. But, there's no reason why it couldn't have been. I'm going to ask a couple questions about this when I'm done. And when I walk around the room, I suspect that I should be able to see the answers on your papers. So you should be able to tell me the acceleration of the object by looking at this. At the same time, you should also be able to tell me if it's speeding up or slowing down. I'd like to know how far the object traveled in the 5 seconds, and what was its displacement in those same 5 seconds. Lastly, assuming the object started from the origin, can you give me a quick sketch of what the position versus time graph would look like? That's what I want. This should take you 5 minutes. If it takes you longer, then you're not keeping up. If this had been our quiz, the scores might not have been particularly high. The slope of a velocity versus time graph is the acceleration. I want to be very clear from the beginning that you have some definitions already that you could have put into play. Now, not all of you did it that way. Some of you realized that there was some data that you could acquire by carefully reading the graph, like an initial velocity of -8 meters per second and a final velocity of 0 in a time of 2 seconds. And so some of you employed a relationship to do this. Fine, but for just a minute, it's got to be this relationship. And if you solve that for A, you get V minus V naught over T, or delta V over delta T. It tells you that it's a slope, right? It's right there. So for a moment, remind yourself that the math has to all say the same thing. It's important for today's lesson that you understand that it's the slope. I'm bringing this up because you get a positive 4 meters per second squared, which many of you got, but then promptly screwed up question 2. The object's not speeding up or slowing down. Now, in the traditional idea, you need to identify the intervals when it's speeding up and slowing down. For the first 2 seconds, it is not speeding up. For the first 2 seconds, it's slowing down because it starts moving at 8 meters per second, and in 2 seconds, it will go from 8 meters per second to 0. That clearly is slowing down. The fact that it's moving in the negative direction doesn't matter. All I was asking is if it's speeding up or slowing down. Now, after the 2 second mark, it's speeding up again. So the first reminder is that positive or negative acceleration does not tell you speeding up or slowing down. You must interpret it from the situation, but the graph clearly indicated that, right? You could have just picked 3 places on the graph and recognized that it was slowing down for part of this and speeding up for the other part. Now, for those of you who got that wrong and didn't write anything down just now, you need a personal invitation for that? Because there's more to go. The object traveled 26 meters. That was not on a lot of papers. During this interval, it's traveling backwards. Using you could use a motion equation for the first 2 seconds if you'd like, or you could just find the area for the first 2 seconds if you'd like. It doesn't matter to me which one you use. You have data, so adding delta x here isn't particularly hard to do. But this is going to come out to be -8 meters. Of course, in this 3-second interval, I can surmise that this is 12 meters per second, right? The velocity was increasing by 4 over the course of 3 seconds, so that's 12 meters per second, making this area 18 meters. I could do that a number of ways. I could make a 3-second interval. I could use the slope, initial velocity, final velocity. I've got lots of data there. Just pick one to tell me delta x, or find the area, 1/2 base times height. Half 12, 6, 6 times 3, 18 meters. So how far did the object travel? It traveled 26 meters. 8 meters in reverse and 18 meters in the forward direction. So the distance traveled 26 meters. The displacement, 10. Right? It is 10 meters away from where it started, because it moved backwards 8 and moved forwards 18. We all good so far? I did not see this on many papers, and this part made me a little bit sad. So let's see if we can just get a quick jot what this is going to look like. If this is position and this is time, let's just move this over so we can see this easier. There, now the people in the back have a fighting chance of seeing it. Well, it starts with a negative slope. So it's got to be something like that. It's got to look quadratic. It's got to demonstrate that it moves backwards, stops, comes back to the origin. That's got to be at the 4-second mark. And then in the next second makes it to the 10-meter mark. The velocity graph and the position graph have to be in agreement. So they have to tell me the same things. So this has got to be, -8, and this has got to be +10. Somewhere right around there. Nothing weird, right? Did I do anything that's weird? It's all the same stuff. Yes, ma'am.
How'd you get that 12 meters per second? Did you do 4 meters times 3 seconds?
I could. Remember, the acceleration says that the velocity changes by 4 meters per second each second. So when I go to second 3, I had to go from 0 plus 4. So right here, it's got to be 4 meters per second. In the next second, so second number 4, I have to increase my velocity by 4 meters per second again. So that's got to be 8. Or, just like you said, I could have said, all right, initial velocity equals 0, final velocity unknown, acceleration is 4 times 3 seconds. That would do it too, right? That would be this interval only. Is that okay? Because, again, I'm trying to make sure you understand all of this has to interwork together. So I could have said initial velocity -8 meters per second, final velocity unknown, acceleration 4 meters per second squared, time interval 5. That should also tell me the final velocity. And yeah, I'd use v equals 4 times 5 minus 8. All good? Again, all of this has to work this way. For one reason, we derived all of it based on just looking at the areas. So it has to work out that it does this kind of stuff. But this one has to be the quadratic because it's a statement of position with time. That's why it has a quadratic function. And this one we know is linear because we started with the idea of a constant acceleration. That means a straight line slope for relating velocity and time. So I expect all of those things, but we still have to interpret it because I have a definition I have to give you today. And it's not ideal, and it's something that I don't want to spend a lot of time on, but I'm afraid that I need to spend some time on it. So let me just get this stuff out of the way. There we go. So there's two definitions that I need you to have in your notes. Be able to refer to them. I said at the very beginning of our discussion here that we would have these qualifiers, instantaneous and average. Everything we've been doing over there has been based on the idea of instantaneous. What is the velocity at a specific point in time? That's what instantaneous velocity means. So in any of these examples, when I said, what is the velocity after 4 seconds? I'm asking for the instantaneous velocity. If I ask for the acceleration at time 3 seconds, I'm asking for the instantaneous acceleration. You could even say instantaneous position because we're talking about something that happened at a specific moment in time. So the word instantaneous means at that instant or at that moment. Average is a whole different world. It's hard for us to do averages for stuff like this because what we're really doing is what's called weighted averages. So there's only two averages that I really want to worry about: average speed and average velocity. And I say that worry about's the wrong word. You just need the definition. But you need to apply the definition when it comes up. They tell us two different things here. And so I want to give you the definition. Average speed is total distance over total time interval. They have to name the time interval. You find the distance traveled. That gives you the average distance. Average velocity, a little different. Total displacement over the total time interval. Two different things and requires two different analyses to get. So when we talk about average speed and average velocity, these are really weighted averages for what happened in the time interval. What we just did would be the work you would have to do to get the information to to calculate average speed and average velocity. For example, the average speed of the object. Well, the object traveled a total distance of 26 meters and did so in 5 seconds. That would be the average speed. However, the object may have never had that speed. Or if it did, it might have done it for just a moment or two. But total displacement, a little different. The displacement was positive 10 meters, same 5 seconds. Meaning that an object with that velocity would get to the same place in the same 5 seconds. Speed one doesn't tell you that, but the velocity one does. So an object traveling at 2 meters per second for a constant 5 seconds would have had a displacement of 10 meters. So these are just two different things. I want you to have them defined, have them in you might have a practice once in a while with them, but they don't show up often. I just wanted you to have their definition. Any question about these two? So we understand now why I'm going to need you to have this together for what we're going to do today, because we're going to be going further than this. So I'm going to change screens real quick. And I want to just put these back. You may want to have these at the ready. So they're already in your notes if you wrote them down. If you didn't, it's fine. I just want to refer to them without having to erase all the other stuff that was there. So our position graph, something like that. And our velocity graph looks something like that. Looking at the velocity graph, just simple questions. Does the object ever have the same velocity twice? No. There's a different velocity for every moment in time. It has the same speed several times, right? Like all of these speeds end up being in the positive direction over there. So it does have the same speed a couple times, but it never has the same velocity twice. On the other hand, is the object ever at the same position twice? Yeah, right. It started at the origin, it goes back through the origin at some point later. So it goes through all of these same positions on the way backwards, and it goes through them all again on the way forwards, right? So it often has the same position twice. These two functions, one quadratic, one linear, have things in common. First, their slopes have meaning. In this case, the slope of this graph tells us the acceleration. And we know that over here, the slope of this graph tells us the velocity. The problem is, put those deltas back. We're still doing deltas. The problem with the position graph is, can we find the slope right there with the tools you have? I mean, do you have those tools? We've talked about what you would have to do. What would you have to do if I wanted to find the slope right there? Put a tangent line. So you do have the tools. You could slap down a ruler. You could get a good estimate for a tangent. And you could then find what the slope of that tangent line is. I'm going to say you have those tools, right? All it takes is a straight edge and your ability to pick 2 points on the tangent line. Fair enough? I need you to learn something new. And that's outside of your algebra class. All of the things that we've done this year, I'm here to tell you we have to do something more than this. And this is what separates AP Physics 1 from mechanics. And I told all of you going in, you would have to learn some new math that you have never learned before. So what we're about to do here is not review. It's something new that most of you have never been taught. The only people who know about this are people who have been through calculus already. And if you're an AB right now, you're not here yet. You're still in the middle of doing limits and stuff, right? Fun times, isn't it? Isn't that lovely homework? No. Well, eventually you're going to get to the fundamental theorem of calculus, which will do what we're about to talk about. But I want to point out something. Raise your hand if you've already finished AB. Anybody in the room? Got the whole one. All right. He has an advantage in that he knows some things, but I also know something very important. Calculus is going to teach you why the things we're going to see work. I don't need you to know why they work. I just need you to know that they work, and you need to believe that. I can kind of prove it. Kinda. You see, we derived calculus from algebra here. The things that we have on the board behind me can be proven using calculus. Proven. But we relied on algebra to create them because that's all you had at the ready. So I tried to use as much of your algebra and geometry skill as possible, and we created all of this from substitution, areas, and slopes. There's another way to do this, the way that is actually in most of the physics books when they were first written. So I want you to pay attention to this. We're going to talk about finding the derivative today, and we're going to define a few things. I would encourage you to take lots of notes here. For those of you who are not in calculus right now, especially if you're in pre-calc, you're going to need to know because there's some vocabulary here. The first thing I want you to understand is that delta works if you're capable of taking 2 points and finding their difference. We're not going to be able to do that because there's no easy way to take 2 points here, find their difference to get the slope. So we're going to talk about a different way to write the delta symbol. It's not much different, but it allows us to find instantaneous slopes in a way that will allow us to find the slope at a single point, even for a curved line. So I'm going to start with the symbology. The symbology is to take the delta and replace it with a lowercase d. This symbology is important because it still represents a fraction, but it suddenly has slightly different meaning. So for the velocity, we say that the velocity is dx over dt. And acceleration, we say that's dv over dt. Now, there is some historical background here, but all you need to understand is that dt represents a very small amount of time, a very small difference in time. And dx is a very small difference in position. Same with dt and dv. They represent a very small difference in time. That's technically what they mean, but they obey all the same rules as fractions. And I need you to understand this. The top is still a small distance, and the bottom, a small displacement. And the bottom is still a small interval in time. That's still true. So I could write this by multiplying both sides by dt. I can treat it like a fraction. So I can cross that out and write dx as v dt. That's okay. It will have other meaning in a couple of days, but this is still the product of two numbers, a velocity and a very small instance in time. That's one thing I want you to know, that these can be treated as a fraction. The second thing I want you to know is the term derivative can be treated as an operation. The term derivative can be treated as an operation. Now that might be new to you, but what it means for us in this class is that you can take the derivative of two sides of an equation in the same way that you can square both sides of an equation, raise both sides of an equation to the same base, add the same thing to both sides of an equation. Taking the derivative is an operation. And to show it as an operation, you'd write it like this. It's the same fraction as before. In fact, I can say v equals the operation of taking the derivative of the function x. In fact, that's how you would say it. This is taking the derivative with respect to time. That's all the stuff on the left. And in here, so when I write it like this, it still represents the same fraction. But what we're saying to the reader, and what I'm saying to you, is that I'm saying that we are going to take the derivative of a function that we have in here with respect to time. Now, I am well aware that you don't really know what it is I'm talking about yet. And I need to train you on that. But the derivative is a process. It's a process you will memorize. We need to know a couple of different derivative rules. You'll be taught 3 of them. And those 3 will be the entire class. That's all we will ever do are those 3. You're going to learn what's called the polynomial rule, the trig rule, and the logarithm rule. So you're going to learn how to take the derivative of polynomials, trig functions, and logarithms. That's all we use them for in this class. That's all we're going to need. So I want to start today by using something we already know. We have a function for position. It looks like this. right? Does this look familiar to you? It's on the board, right? It's this one. All I've done is take the delta x and move x naught to the other side. Now, this is an important question, and you need to be really paying attention to understand this. Is x a function based on time? Meaning, will this equation give me the position of an object for different moments in time? Now, if you don't know what I'm asking you to look right here. Is t a functional variable in our equation? Could you plug in different t's and get different positions? Okay? Now, this part's hard. I know it is. So please hear me out. We're trying to find a way to get the slope without having to put in tangent lines all the time. This is a quadratic. The slope is always changing, right? So for every single t, there's a different slope. I want to find the slope without having to put a tangent line in for every single point on the function. That's what this is supposed to do. Because if I take the derivative of both sides with respect to t, let's just write it out. The derivative of both sides with respect to t. Notice I'm treating this like an operation. I'm operating on the equation. It's kind of like I said before, like if I was squaring both sides, I'd put in parentheses and put a little square on top of it. I'm applying the derivative to both sides. The left side, we know what this is. It was just up here, right? The left side says if I take the derivative of the position function with respect to time, I get the velocity. It's a definition. So in this equation, this will be the velocity because that's how it's defined. The derivative with respect to time of the position. Now this next side, you don't know what to do because you don't know how to take derivatives. That's what we're going to learn here. And we're going to learn what's called the polynomial rule. I want you to understand a couple things about derivatives. First, derivatives obey the distributive property, which means they can be distributed in an equation. Next, for every different type, help me out here. Sorry, got lost. For every single type of function, there's a way to take its derivative. This is a polynomial function. And you guys know what polynomials are, right? This is a nomial, a term. There's multiple terms connected by pluses or minuses. That's what makes it a polynomial. It's a function that has time as a major variable. It shows up here, here. Doesn't show up here, does it? So if you have one where there doesn't seem to be a polynomial that exists, that doesn't have the same variable in it, like we're trying to focus. This says I want to take the derivative with respect to time. So the first thing I want to highlight to you is that when you're taking the derivative with respect to a variable, that variable becomes the thing that you're looking at. Everything else is a constant. It's just a number. So you don't ignore it, but the constants are not what you're interested in. The variable that's on the bottom is what you're interested in. We are taking the derivative with respect to the time. So the time becomes important. Everybody following along okay? Next, and this part's incredibly important. For every single kind of function, there is a derivative. And polynomial, it's just a process. But if you see one in here like this, where one of the terms does not have a t in it, add a t to the 0 power. Because t to the 0 power is just 1. In fact, you might find this easier to put in the 1 for t. Now I have a second order polynomial. t squared, t to the first power, t to the 0 power. All right. An aside, I'm doing this on purpose using different letters. If I was taking the derivative with respect to b of cb to the n power, and I'm just randomly choosing letters. Okay, if I'm taking this derivative, c doesn't matter, it's a constant. So just put c on the outside and focus on just this part. The derivative with respect to b is a process, and it looks like this. You take the exponent, put it out front, and then subtract 1 from the exponent. Yep.
What is C?
Just a constant.
It's just
Just something that's not b. Okay. Then simplify. But this is it. That is the derivative of a polynomial. Let's see what that would mean here. The first term has 1/2 a in front of it. None of those are t. Yeah?
No, I was just never mind.
Okay. None of those are t. So I'm going to put the 1/2 a out, and I'm going to take the derivative with respect to time of t squared plus v naught times t to the first power. V naught is not t. Okay. Plus the derivative of t to the 0 power. X naught is not t, so I've distributed the derivative, applied it to each term in the polynomial. Now I'm going to apply the process. Bring down the exponent, subtract 1 from the exponent. So 1/2 a times 2t to the 2 minus 1 plus v naught, bring down the 1 times t to the 1 minus 1 plus x naught times, bring down the 0, t to the 0 minus 1. So everybody see what I did? I brought the exponent out front and then subtracted 1 from the exponent. I did that in every single term. So I had a 1 here, I brought it out front, and I subtracted 1 from the exponent. Everybody okay? I brought the 0 down, subtracted 1 from the exponent. That's what this said. This was the process. And I said, follow the process. We ignore the constant. Put the constant out front, get it out of the way. Now, I know the bell's probably about to ring or has. Simplify. 2 times 1/2 is 1. So a t to the 2 minus 1 is just a t. Plus t to the 1 minus 1 is t to the 0 power, which is 1 times 1 is plus v naught. 0 times t is, doesn't matter, that's t to the negative 1 power. 0 times it makes it go away. 0 times x naught is, and out front was just v. You see it, right? That's how calculus works. That's how they're related.